another very important statement that we have in many programming languages is the case statement or switch statement. So, a typical case statement will look something like this. We have got a, for example, in the C language we have got this switch statement, switch some boolean, some expression, and then we have got different cases. So, case 0, case 1. So, like that there can be different cases and there is a default case also. Now, as we know that this case statement can be modified into some if then else a bunch of if then else statement. Like first you have the code for evaluating. So, if you take this as the format, first you have the code for evaluating E and then you have this type of code. So, if the final value is available in E dot place. So, if E dot place equal to C1. So, if whatever be that E dot place equal to C1, then go to some code, else again another if, etcetera. So, this way you can generate a set of nested if then else statements and you can generate the corresponding corresponding case statement code. So, you can have different implementation alternatives, like you can have a linear search for the matching option, like for after you have evaluated E, you can have a search and you can say that if this particular number is matching, if the particular case value is matching with the value of the expression, then we will go to that option. So, that is a linear search type of matching. You can have a binary search for matching case, because if we assume that these cases, so they are all going in ascending order, then I can do a binary search after evaluating this into some temporary t. So, you can search for t into these alternative values C1, C2 up to Cn. So, try at the middle and then that is the binary search. So, if it matches with t, that is fine. If it is less than t, if t is less than this the middle value, then you search in this portion of the array, otherwise you search in the other part of this array. So, that was the binary search principle. So, here also you can have a similar search principle. So, after that you have some sort of a jump table. So, what is a jump table? So, jump table structure is like this. So, I have got a table. Okay. So, in this table there are two columns. So, one column is the value of this switch, value of E, and this is the 3 address code index, 3 address index. Now, in the code part I have got, so here if I say that this block is S1, this block is say S2, like that. So, in the code file I have got these codes, like so here I have got the code for S1, here I have got the code for S2, S3, like that. Now, if this start address is say x1, so this start address is x2, this start offset is x3, like that. So, you can have a table where C1 is x1, C2 is x2, C3 is x3. So, you can have this type of table. Now, so this we call a jump table, because so by consulting this table you can figure out where to jump. Okay. And now, we have to search through this table to get the jump target, that is x1, x2, x3, etcetera. Now, that is what I can search. I can search using a linear search method. I can try match with all these values one by one, or we can do a binary search as I was telling. So, you can probe at the middle of the table, see whether the value is equal or less or greater, and accordingly you can do that search. And as you know that linear search, so this has got a complexity of order n if there are n alternative cases, whereas the binary search will have a complexity of order log of n for n number of cases. Now, this jump table structure is good and this linear or binary search is cheaper if number of cases small. Okay. However, for this larger number of cases, so jump table may be cheaper, because so this so the other implementation that you can do is that you can just instead of doing in the jump table, instead of keeping all these values here directly, so you can use another type of jump table where it is like this. I do not keep the value of this C1, C2. So, they are implicit, the values of C1, C2 are implicit. So, suppose this value of this expression, it can go in the range from say 0 to say some maximum max. So, I have got a table where these indices they run from 0 to max, fine, and then at so assuming that there is a case for case 0 and that is x 1. So, I write x 1 here. So, for 1 if the value is 1, suppose the jump target is x 2. So, I write x 2 there. So, for 2 it may be x 3, for 3 it may not be there, case 3 may be absent, case 4 may be something say x 10. So, like that. So, there are so now what happens is that you do not need to do a linear search or binary search at all. So, once you have evaluated the expression E, so you can use it directly to index into this table and say this particular ET. So, suppose this E evaluates to this particular index. So, you take the jump target from here and go to that particular address. So, that way we can have a very efficient jump table implementation rather than searching through the index values. Now, this is good if the number of cases are the number of cases are large. So, that way the jump table may be cheaper. However, it may so happen that numbers are more, but this the values are so all the cases are not present, in the sense that this max may be a very large number. So, this may be say 10,000, okay, but the actual cases that you have are having say case 1, 5, 100 and say 250 and 10,000. So, these are the only few cases, but if you are thinking about this type of implementation, then you have to keep a table with 10,000 indices, whereas if you are doing a if then else. So, this type of realization where you will be comparing with each and every location and then come to a decision. So, that way the table may be compact. So, this is a trade off between this normal implementation with linear search and a pure jump table based implementation. So, depending upon the choice of the compiler designer, so they can go for either of these two options. So, it depends on the type of programs that are being written in the system. Okay. So, this is the jump table implementation procedure. So, if maximum and minimum case values are C max and C min respectively. So, first you have a code to evaluate the expression E into some t. So, first you have the code. So, in this part you evaluate t, and ultimately this local variable t has got this E dot place. So, t corresponds to E dot place. So, you have this thing. Now, there are default cases. So, if this t happens to be less than C min or t happens to be more than C max, that means that they will not match with any of the entries in the jump table. So, they will go to the default case. Otherwise, it will as I was telling. So, it will be consulting one particular entry in the jump table. So, if this is the corresponding jump table, so it will be consulting this particular jump table, and this t value will be used to index into this table, and suppose it picks up. So, this particular entry and goes there. So, that way I will have this jump table t go to jump table t. Otherwise, this default case, so this label will be there, and this go to statements. So, that will take the default statement default part execution like this. So, jump table I, so it will contain the address of the code to execute if E evaluates to I. So, that is the jump table implementation. So, we can so these are the alternatives that are done in realizing this case statements in programming languages for the 3 addressed code translation. Next, we will be looking into the function calls. So, function calls, they can be divided into 2 subsequences. So, calling sequence and the return sequence. So, calling sequence is the set of actions that are to be executed at the time of calling a function, and return sequence is the set of actions to be executed at the time of returning from the function call. Though it appears to be pretty simple, that you just note down the return address, keep it in the stack and go back, go to the function, and while coming back just take the return address from the stack. But that is not all, as we have seen that this runtime environment management. So, it tells that you have to do many things for supporting recursion and all. So, that way you need to do many actions. So, there will be a set of actions at the time of returning from the function also, at the time of going to the function also. And these actions are also distributed in the sense that some part of the action which should be taken by the caller function and the other by the callee function. So, both of them have got definite role to play for generating these function calls, implementing the function calls. So, what are the responsibilities for the calling sequence? So, caller for the calling sequence the responsibilities are like this. The caller it is going to call the callee routine. Okay. So, in the process, so before going to the callee routine, so it will be first evaluate the actual parameters, then place actuals where the callee wants them, then corresponding 3 address instruction is the parameter t, then save machine status state, that is current stack and or frame pointer, return address, etc. and the corresponding 3 address instruction is call pn, where n is the number of actuals. So, what do we mean by this? So, maybe I have given a call to a procedure or a function say x equal to say function 1, and there I am passing the parameters like x, y plus z, star p, like that. So, these are the, suppose these are the 3 parameters that are passed. Now, this x, y plus z and star p, they need to be evaluated first. Okay. So, they are evaluated. So, this x may be current value is 10, y plus z current value may be say after evaluating this expression. So, this may be 15. So, that way I should have some code for evaluating these expressions. Okay. And then this star p, so it has to, this is a pointer access, so it has to go to the corresponding location and get it. Sometimes we need to change, send the address of a particular variable. So, we send it like ampersand x. So, then the this has to be evaluated. So, address of x has to be found out. So, that evaluation code has to be there. So, this evaluate actual parameters, though it is very simply written. So, but it involves some proper amount of code, and in fact, one parameter passing the parameter that I am passing, that itself may be another function call. So, that way it becomes more complex, fine. So, we place the, so after we have evaluated them, then we have to place the actuals where the callee wants them. So, where will the callee want them? So, normally for this runtime environment management, we have seen that the activation records are there. So, the activation record will be created and all the parameters, so they will be put into the activation record. From the 3 address code point of view, so we will call it as parameter t. So, if there are 3 parameters, so there will be 3 parameter statement, param say t1, param t2 and param t3. So, but the idea is that this param t1, t2, t3, when they are executed, so they will actually be copying these values of these parameters onto the activation record slots, and after that it will save the machine state. So, current state and or so frame pointer, return address. So, whatever is required by the operating system, whatever is required to return from one procedure call and all. So, it will be saving all those information into the into some proper place. So, it may be stack, it may be some other memory location, etc., but it will do that. And then accordingly the corresponding 3 address code level. So, just to model this phenomena at 3 address code level, we will have the statement call p n. So, it is calling the procedure p with n number of actuals, n number of parameters. So, that is the thing that will be done at the caller end. At the callee end, so it will save registers if necessary. So, if the caller has not saved registers and it is necessary that this whatever register this caller had, so that should not be disturbed. So, it will first save the CPU registers into some memory locations, then update stack and frame pointers to accommodate m bytes of local storage, because at this point the callee routine knows like how many bytes of local storage it has, all the variables that are defined in this. So, it was not possible at the caller point, because caller will not know like how many parameter, how many local variables the callee routine will have. But once we are in the callee routine, so we know that when the callee routine is parsed, so by that time we know what is the number of parameters that are that number of local variables that are going to be there in the procedure or in the function. So, accordingly it will accommodate m number of bytes of local storage, and corresponding 3 address code that we will be using is enter m. So, at 3 address code level we keep it simple, because this is a very machine dependent feature. So, we do not want to go into much detail of it. So, we just keep a note that enough actions are to be taken, so that they are created in this fashion. So, this all the local variables are created there. So, that is about the calling sequence. Now, for the return sequence, so it is just the other way. So, the callee routine, so it will place the return value if any where the caller wants it. So, normally as we know that in the activation record, so there is a slot for this return value. So, depending upon that setting, so it will be putting this return value onto that particular slot. It will adjust the stack and frame pointers. So, maybe that pointer are to be reduced or increased, whatever it is. So, it has to get rid of that frame and all. So, all those things are done by adjusting the stack and frame pointers. Then it will jump to the return address. So, this it will take the return address from the activation record and it will jump to the return address. So, the callee that way the callee will come back from the from it to the caller routine, and the corresponding 3 address instruction is return x or return. So, this return x, it will be returning the return value x, and this simple return. So, this is a void type of return. So, there is nothing, there is no value that is returned. So, it is a void procedure call. On the other hand, if you look into the caller, so it has got the responsibility to save the value returned by the callee. So, callee has returned some value into some variable, into some slot in the activation record. So, that has to be saved into some register or into some variable. For example, it may be like say x equal to some function f1 etc. So, at the end, so this function once activation record, so it will have this return value somewhere. So, that value has to be copied into x. Okay. So, for that matter, so it has to generate 3 address code where some temporary will be equal to this return value, and then this x will be equal to that temporary. So, something like that has to be done. So, the corresponding 3 address instruction is retrieve x. Since we do not know from which how this return value will come exactly in the target machine language. So, we just keep it this retrieve statement. So, the caller, it will be retrieving the return value from the activation record. Now, how will it retrieve? So, those things are not known at this point, because that is very much machine specific. So, next we will look into an example how this function call will take place. So, this x equal to f0 y plus 1. So, these are the 2 parameters passed and minus 1. So, this first it will be evaluating the parameters. So, you see that the first statement was to evaluate the actual parameters. So, first that evaluation is being made t1 equal to y plus 1 param t1. Then for the next next parameter is 0. So, that is also evaluated. So, that is param 0. Then it is call f and the number of actuals, like how many parameters are passed etc. So, how many local variables are there. So, all those are taken care of. So, call f2. Then after calling after returning, so here I do not have the code for f in this particular piece of statement. So, I assume that code will be coming somewhere else, but after returning from that code, so the caller routine, so it has to retrieve the value from the return value from the activation record. So, that is retrieve T2, it is expected to do that. So, it will be retrieving the value from the activation record, and then T3 equal to T2 minus 1. So, it will be retrieving, it will be doing the computation. So, after T2 has come, so this this f0 f0 y plus 1. So, this is available in T2. So, this T2 minus 1. So, that is made equal to T3, and this x is finally equal to T3. So, this is the 3 address code generated for the parameter part, for the function call sort of thing. So, that makes it the caller side. Now, for the callee side, so there we have to do the storage allocation part. Okay. So, because these the local variables are to be created and all. So, but here is a problem, because as the first instruction in a function is enter n. So, enter n, so it will create space for the locals, temporaries, etc., and value of n is not known until the whole function has been processed. So, how much local space has to be allocated, so that is not known at this point. So, the typical situation that we can think about is, maybe this is a function, say integer f1, it has got some parameters, and into this I have got the local variables like say integer x and y, and I write some expression involving x, y, etc., x equal to y plus some parameters passed a, b, say x plus a into b, then y equal to y plus 15, then again x equal to say x divided by say y plus 19. So, like that there may be a number of statements. Now, one thing that is clear, that for this x and y we need space. So, for them we can calculate the space, but the difficulty comes because for this expression x equal to y plus a into b. So, this is not a single, so the for this, so this whole computation cannot be done at once, okay, because 3 address code we have assumed that there are only 2 operands per instruction per computation. So, it has to be done like T1 equal to a star b, then T2 equal to y plus T1, and then x equal to T2. So, that way this extra 2 temporaries T1 and T2 have got created. Similarly, for this statement or this statement also, so other temporaries will get created. Now, when these temporaries are getting created, so this is not known at this point. Okay. So, so until and unless I have seen this entire function, I do not know how many temporaries will be coming. So, it is not known, the value of n is not known until the whole function has been processed. So, how to handle this situation? So, there can be 2 possibilities. So, either we can generate final code in a list. So, we can say that instead of writing quadruples onto the file, the code quadruples onto the file, we just keep them in a list. So, so this we have got the first statement as enter statement, and this it will have another part which is the n part, which is not known, and then I point to the next statement block. So, next statement block that are generated, so they are kept in a linked list. So, at the end of this entire code generation, I will know the what is the value of n. So, how many bytes of storage is necessary, then I will backpatch, so this location with that particular value. Okay. And then so then after that this whole code will be written onto the code file, the intermediate code file in this order. So, that is one possibility. So, generating the final code in a list, so that I can do all these corrections, and then I can just dump it onto a file. Other possibility is to use a pair of go to statements. So, use a pair of go to statements, so you can solve this problem. So, we will see how this can be done. So, this is the part which is generating final code in a list. So, generate final code in a list and backpatch the appropriate instructions after processing the function body. This approach is similar to single phase code generation for Boolean expression and control flow statement. So, in single phase generation also we have seen that we are producing the codes, and after that we are doing some backpatching. So, here also I am telling the same thing, you generate the code in a list and after that you do a backpatching of them, backpatching of the code. So, that is one possibility. So, it is possibility of machine dependent optimization. So, that is one advantage. So, you can do many optimizations, so which are dependent on the machine. So, you can modify the statements accordingly, but it may be slow and may require more memory during code generation. So, this linked list type of organization, as you know, that as far as access is concerned, so it is going to be slow, because it has to traverse through this dynamic memory and all. So, it takes time. And the second thing is that the memory requirement is also more, because the amount of space necessary for holding the pointers, so they will come into the picture. So, this final code generation using this approach is difficult. So, using a pair of go to, so the code, so this is an example. Suppose we have got a function called foo, and in this function we have got So, at the beginning of the function we generate a go to L1. So, in the here I have put the code for enter n. So, that will be put into this L1 part. So, while generating the code, so we just do it like this. So, we generate a label. So, at this point we generate a new label and we put it we generate a go to statement at this point. So, this is the now we generate another label L2 and we call it like this. So, they are the code for the body of foo is presented. So, here I have got the body of the procedure. Then at L1, so once we are at this point, once the entire procedure and entire function has been generated, the code has been generated, we know how many temporaries were used. So, what is the space requirement and all. So, I can have this code for enter n. So, this n value is now known. So, I can have the enter n thing, and after that we generate a go to for L2. So, it comes here. So, how the whole function works. So, as soon as it is called, so it will be starting with this go to statement, it will come here. So, it will have the code for enter n. So, that there it will be allocating enough space for the temporaries and all, and then it will come to this statement go to L2. As a result, it will come here and start executing the body of the function. So, this way using a pair of go to statements we can solve this local parameter local variable issue. So, next we will be coming to the conclusion. So, we have seen a number of intermediate code generation mechanism. So, it is though intermediary code generation is not mandatory, it helps in detargeting the compiler towards different architectures. Now, selecting a good intermediate language itself is a formidable task, because they have to be equally distant from the source language and the target language. 3 address code is one such representation that we have seen. It is very versatile and it is very powerful that way, and syntax directed schemes are best used for generating the 3 address code from the parse tree of the input program, and translation of almost all major programming language constructs we have seen, and we can do this translation using them. So, after this intermediary code has been generated, so you can go to the code optimization phase, the target code generation phase, followed by code optimization. Now, the target code generation is nothing but a template substitution. So, for each intermediary code template, so you can think about a best way to implement the target code for that, and accordingly you can generate code for that, and also the optimization part. So, you can do some optimization at the intermediary code level itself, like you can find that the same sub expression is being computed again and again. So, they can be computed only once, put into some temporaries and used there, or maybe some computation you can find out that it is not necessary, because it is maybe carried out in a loop, but it is not dependent on the loop index. So, they can be taken out of the loop. So, this type of optimizations can be done at the intermediary code itself. However, more important type of optimizations, like say putting the variables into registers and all. So, that will be difficult, because that will require the exact machine architecture, and that can be done only at the target machine level. You cannot do it at intermediary code, because you do not know how many registers you will have. So, this way, so the later part, or the more advanced concepts on this compiler. So, they will be discussing about this optimization issues, this target code generation issues and all. So, we will end our theory class with this. So, we will be doing some more exercises in the next classes.